Facts about the universe to fall asleep to. Hello and welcome. I'm so glad you're here with me tonight. Perhaps it's been a long day, or maybe you simply enjoy drifting off while contemplating the quiet wonders of existence. Either way, this journey is for you. There's nothing you need to do right now except let your body settle, your breathing slow, and your thoughts begin to wander freely. Tonight, we're exploring the universe itself, not just one galaxy or phenomenon, but the vast, gentle expanse of everything that is. We'll move slowly from discovery to discovery, touching on black holes, ancient light, the invisible scaffolding of dark matter, and galaxies so distant their light began traveling toward us before Earth even existed. Some of these ideas may surprise you. Others might accompany you softly into sleep, becoming part of your dreams. And if this peaceful exploration helps you rest, feel free to like and subscribe. It helps others find their way here too, to this calm place where science meets stillness. Now, if you're ready, let's begin. The architecture of everything. The universe is older than most current estimates suggest, or perhaps not quite as old as some observations indicate. Most astronomers place its age at about 13.8 billion years. This figure emerges from measurements of the cosmic microwave background, that faint afterglow of the Big Bang, and from careful observations of how quickly space is expanding. But not all measurements agree perfectly with one another. Some ancient stars and distant galaxies appear to be older than this estimate comfortably allows. Others question whether the expansion rate we measure today has remained constant, or whether dark energy, that mysterious force pushing galaxies apart, might have changed its behavior over cosmic time. These tensions haven't been resolved. The 13.8 billion year figure remains widely accepted, but the questions linger like whispers in the dark. Could the universe be older than we think? Did we miss something fundamental about how time and space behave across such immense scales? It's entirely possible that what we call the beginning, the Big Bang itself, was just one chapter in a much longer, stranger story. When you look up at the night sky and see stars scattered across the darkness, you're seeing just the tiniest fraction of what actually exists. The universe has structure on scales so vast they defy easy comprehension. Galaxies aren't scattered randomly through space. Instead, they gather along enormous threads of dark matter and gas, creating what astronomers call the cosmic web. These filaments stretch for hundreds of millions of light years, connecting massive clusters of galaxies and leaving enormous voids in between. The voids are nearly empty, vast bubbles of darkness where very few galaxies exist. The filaments, meanwhile, act like highways where galaxies form and travel. This web-like pattern emerged from tiny fluctuations in the early universe, quantum ripples that were stretched to cosmic proportions during the first fraction of a second after the Big Bang. What began as the smallest possible variations in density became the largest structures we know. When scientists mapped the positions of millions of galaxies across huge swaths of sky, this pattern emerges clearly. Dense nodes where many galaxies cluster together, connected by thread-like structures, with vast empty regions in between. The resemblance to a neural network is striking, though purely coincidental. The universe isn't conscious, but the same mathematical principles that govern how matter clumps under gravity also seem to shape patterns in biological systems. It's a reminder that certain structures appear again and again at different scales, from the microscopic to the cosmic. The observable universe, that sphere of space from which light has had time to reach us, extends about 46 billion light-years in every direction. You might wonder how it can be 46 billion light-years across if the universe is only 13.8 billion years old. Shouldn't light only have traveled 13.8 billion light-years? The answer lies in expansion. While light was traveling toward us, space itself was stretching, carrying those distant galaxies even farther away. So the light we see today from the most distant galaxies left them when they were much closer, but during the journey, the expansion of space increased the distance dramatically. This creates a kind of cosmic horizon. Beyond this edge, there are certainly more galaxies, more stars, perhaps stretching infinitely, but their light will never reach us. The expansion of space carries them away faster than light can close the gap. Every year, more of the universe slips beyond this horizon, fading from view not because the galaxies themselves disappear, but because the space between us and them grows too quickly. One day, trillions of years from now, galaxies beyond our local group will have receded so far that future astronomers won't even be able to detect them. The visible universe will shrink, not through destruction, but through distance and time. The universe might also lack any true edge in another sense. According to general relativity, space itself can be curved by matter and energy. Current evidence suggests that on the largest scales, the universe appears to be either flat or very close to flat, which might mean it extends infinitely in all directions. Alternatively, it could be curved in such a way that it loops back on itself, like the surface of a sphere, but in more dimensions than we can easily visualize. If that's the case, you could theoretically travel in a straight line forever and eventually return to your starting point, not by hitting a boundary, but by following the curvature of space itself. Either way, flat and infinite or curved and closed, the universe has no edge in the traditional sense. No place where space suddenly stops and something else begins. This can be difficult to picture, but think of it as similar to asking what's north of the North Pole. The question itself doesn't quite make sense within the geometry involved. The universe is all of space, all of time, the complete container for everything that exists. There's nothing outside of it to speak of, no beyond. Just the gentle, endless expanse of existence itself. Dark mysteries that shape reality. Most of the universe is invisible. When you look at images of galaxies, you're seeing stars, gas, dust, all the luminous matter that emits or reflects light. But this visible matter makes up only about 5% of everything that exists. Another 27% is dark matter, a substance that doesn't interact with light at all. It doesn't emit, absorb, or reflect electromagnetic radiation in any form. We know it exists only because of its gravitational effects. Galaxies rotate too quickly for their visible matter alone to hold them together. They should fly apart, but they don't. Something invisible is providing additional gravitational pull. Clusters of galaxies show the same effect. Light from distant objects bends more than it should when passing through galaxy clusters, revealing the presence of hidden mass. This bending of light, called gravitational lensing, has become one of the most powerful tools for mapping dark matter's distribution. Scientists can create maps showing where dark matter is concentrated even though they can't see it directly. These maps reveal halos of dark matter surrounding galaxies, vast cocoons of invisible mass that extend far beyond the visible edges. Recent work from the Dark Energy Survey and the Dark Energy Spectroscopic Instrument has measured the shapes of over 100 million galaxies to probe how dark matter influences cosmic structure. By analyzing tiny distortions in galaxy shapes caused by weak gravitational lensing, researchers can infer the distribution of mass across enormous volumes of space. These surveys have confirmed that dark matter follows the predictions of the standard cosmological model remarkably well. The universe grows clumpier over time as gravity pulls dark matter and ordinary matter together, but not too clumpy. The rate of structure formation matches what we'd expect if the universe contains about 27% dark matter, 5% ordinary matter, and 68% dark energy. These proportions have been verified by multiple independent methods, from the cosmic microwave background to galaxy surveys to supernova observations. The consistency across different techniques gives scientists confidence that the overall picture is correct, even if the fundamental nature of dark matter remains unknown. What is dark matter made of? That's one of the great mysteries. The leading candidates are weakly interacting massive particles, or WIMPs, hypothetical particles predicted by extensions to the standard model of particle physics. These would be heavier than protons, but interact so weakly with ordinary matter that trillions could pass through your body every second without you ever noticing. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, hopping to catch the rare collision of a WIMP with an atomic nucleus. So far, no confirmed detection, though a recent analysis of data from NASA's Fermi Gamma Ray Space Telescope may have found evidence of WIMPs annihilating near the center of our galaxy. When two WIMPs collide, theory suggests they should annihilate each other, releasing high-energy gamma rays. A researcher at the University of Tokyo detected a halo of gamma rays with exactly the energy and distribution expected from WIMP annihilation. The signal closely matches models predicting WIMPs with a mass about 500 times that of a proton. If this detection holds up under scrutiny, it would be the first direct observational evidence of dark matter particles, a discovery that would reshape both astronomy and physics. Another candidate is the axion, a hypothetical low-mass, low-energy particle first proposed to solve a problem in quantum chromodynamics. Axions would be much lighter than WIMPs, and there would be vastly more of them, forming a kind of invisible wind blowing through the galaxy. Detecting them requires different techniques, often involving strong magnetic fields that might convert axions into photons. Several experiments are underway, though none has yet provided definitive evidence. There are also more exotic possibilities. Perhaps dark matter isn't a particle at all, but a modification to our understanding of gravity on cosmic scales. Some theories propose that gravity behaves differently than Einstein's general relativity predicts when dealing with very weak gravitational fields like those found in galaxy outskirts. These modified gravity theories can explain some observations without invoking dark matter, but they struggle to account for others, particularly gravitational lensing in galaxy clusters and the patterns in the cosmic microwave background. Most physicists favor the particle dark matter hypothesis, but the door remains open to alternatives. Then there's dark energy, even more mysterious than dark matter. In 1998, two teams of astronomers made a shocking discovery while studying distant supernova. They were trying to measure how much the universe's expansion had been slowing down over cosmic history. Everyone expected gravity to be gradually breaking the expansion, pulling galaxies back toward each other. Instead, they found the opposite. The expansion is accelerating. Distant supernova appear fainter than they should, indicating they're farther away than expected for their redshift. Something is pushing space apart, working against gravity. This unknown force was dubbed dark energy, and it appears to make up about 68% of the universe's total energy content. The simplest explanation is Einstein's cosmological constant, a term he introduced into his equations to allow for a static universe, then abandoned when Hubble discovered cosmic expansion. The cosmological constant represents a fixed energy density of empty space itself. As the universe expands and space grows, the total amount of dark energy increases, while ordinary matter and dark matter become more diluted. This leads to accelerating expansion. Recent data from the Dark Energy Spectroscopic Instrument, which has mapped over 6 million galaxies and quasars, hints at something potentially more interesting. Instead of remaining constant, dark energy's density might change over time. The data fits slightly better to a model where the relationship between dark energy's density and pressure evolves, though the evidence isn't yet definitive. If confirmed, this would require a more complex explanation than the cosmological constant, perhaps involving new fields or forces. It would also dramatically affect predictions about the universe's far future. A constant dark energy leads to eternal accelerating expansion, gradually cooling the cosmos into cold darkness. But if dark energy's strength changes, other fates become possible. The expansion could slow again, or dark energy could grow stronger, eventually tearing apart galaxies, stars, planets, even atoms in a catastrophic Big Rip. Alternatively, dark energy could weaken and reverse, causing the universe to collapse back into a big crunch. For now, the simplest model still fits the data well, but scientists are keeping an open mind. The universe has surprised them before. As you lie here, consider this. Dark matter is passing through you right now. Your body, this room, the Earth, All of it sits within a vast halo of invisible particles. Trillions stream through every square centimeter every second, moving at hundreds of kilometers per second as Earth orbits through the galaxy's dark matter distribution. They interact with ordinary matter so weakly that they pass through the entire planet as though it were made of nothing. To them, all the atoms that make up your world might as well not exist, and yet their gravitational influence shaped the galaxy we inhabit. Without dark matter, the Milky Way wouldn't have formed. Stars and planets wouldn't exist. The invisible has always been here, silent, ever-present, essential. It's woven into the fabric of existence as surely as the atoms in your bones, even if we can't see it, touch it, or fully understand it yet. Stellar extremes. Stars come in an astonishing variety, from dim red dwarfs that burn for trillions of years to massive blue giants that exhaust their fuel in mere millions. But among the most extreme objects in the universe are neutron stars, the collapsed cores of massive stars left behind after supernova explosions. When a star about 8 to 20 times the mass of the Sun runs out of fuel, its core collapses in a fraction of a second. Electrons and protons are crushed together, forming neutrons. What remains is a sphere only about 20 kilometers across, but containing more mass than the Sun. A sugar cube of neutron star material would weigh about 1 trillion kilograms on Earth, roughly as much as a mountain. The gravitational pull at the surface is 100 billion times stronger than Earth's. If you could somehow stand there, you'd be flattened instantly, compressed to less than a millimeter thick. Even light has difficulty escaping. Photons lose energy climbing out of the gravitational well, getting redshifted to longer wavelengths. These objects spin rapidly, often multiple times per second, because as the core collapses, conservation of angular momentum causes the rotation rate to increase dramatically. It's the same principle that makes ice skaters spin faster when they pull their arms in, taken to an almost unimaginable extreme. The fastest known pulsar, PSRJ 174824446 AD, rotates 716 times every second, or 43,000 revolutions per minute. That's roughly twice the speed of a typical kitchen blender, but we're talking about an object the size of a city with more mass than the Sun. Points on its equator move at about 20% the speed of light. At that speed, general relativity becomes essential for describing what happens. Space and time are warped dramatically, and the star bulges outward at the equator, forming a shape more like an oblate spheroid than a perfect sphere. Neutron stars also possess intense magnetic fields, often trillions of times stronger than Earth's. These fields channel particles from the star's surface into narrow beams that shoot out from the magnetic poles. As the star spins, these beams sweep through space like the light from a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam crosses our line of sight. These objects are called pulsars, and they were first discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University. She was using a radio telescope to study how radio waves from distant cosmic sources twinkled as they passed through the solar wind. During her observations, she noticed several sources that pulsed with extraordinary regularity, about once per second. The signals were so regular and precise that she and her colleagues briefly considered the possibility they might be artificial, signals from an extraterrestrial civilization. They even labeled the sources LGM, for Little Green Men. But soon, they found more pulsars in different parts of the sky, and the hypothesis that they were natural objects, specifically rotating neutron stars, gained overwhelming support. Pulsars have become some of the most useful tools in astronomy. Because they pulse with such remarkable regularity, more accurate than atomic clocks over long periods, they can be used to test fundamental physics. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar in a binary system with another neutron star. The two objects orbit each other every 8 hours, moving at incredible speeds, and general relativity predicts that such a system should radiate gravitational waves, losing energy and causing the orbit to gradually shrink. By carefully timing the pulsar's pulses, Hulse and Taylor measured this orbital decay and found it matched Einstein's predictions perfectly. This was the first indirect evidence for gravitational waves, decades before they were directly detected. The discovery earned them the Nobel Prize in Physics in 1993. Some neutron stars are even more extreme. Magnetars have magnetic fields about 1,000 times stronger than typical neutron stars, reaching strengths of 100,000 trillion Tesla. That's so intense it can distort atoms themselves, stretching their electron clouds into elongated shapes. If you were within 1,000 kilometers of a magnetar, its magnetic field would be strong enough to disrupt the molecular bonds in your body, essentially pulling you apart at the atomic level. Fortunately, magnetars are rare, and we don't know of any within tens of thousands of light-years of Earth. These objects are also young, only thousands to tens of thousands of years old. Their intense magnetic fields gradually decay over time. As they lose their fierce magnetism, they settle into more ordinary neutron stars. But while their fields remain strong, magnetars can be spectacularly violent. They occasionally undergo starquakes, sudden fractures in their rigid crusts caused by the stress of the magnetic field. These quakes release enormous bursts of X-rays and gamma rays, brief flashes of radiation so intense they can be detected across the galaxy. In 2004, a magnetar called SGR 180620, located on the other side of the galaxy about 50,000 light-years away, produced the largest burst of radiation ever recorded from an object beyond our solar system. The flood of gamma rays arrived at Earth on December 27, disrupting satellites and ionizing the upper atmosphere. For a tenth of a second, this distant magnetar released more energy than the Sun emits in 100,000 years. The flash briefly made SGR 180620 brighter than the full moon in gamma rays. If this magnetar had been just 10 light-years away instead of 50,000, the radiation burst might have caused a mass extinction on Earth, stripping away our ozone layer and exposing the surface to harmful ultraviolet radiation. It's a sobering reminder that the universe contains forces far beyond anything we experience in our protected corner of space. Neutron stars also exist in binary systems with regular stars, and these pairings create their own fascinating phenomena. When a neutron star orbits close to a normal star, its gravity can pull material from the companion's outer layers. This stolen gas spirals down onto the neutron star, forming a glowing accretion disk that shines brightly in X-rays. As matter accumulates on the surface, conditions become hot and dense enough for nuclear fusion to ignite explosively, creating what's called an X-ray burster. These are like thermonuclear bombs going off on the neutron star's surface, releasing as much energy in a few seconds as the Sun emits in a week. The neutron star survives unscathed, ready to accumulate more material and explode again days or weeks later. Some neutron stars in binary systems become millisecond pulsars, spinning hundreds of times per second. These likely started as ordinary pulsars that had slowed down over millions of years as their magnetic fields weakened and their rotation gradually braked. But when they began accreting matter from a companion star, the infalling material pushed on the neutron star's surface in the direction of rotation, gradually spinning it up again like a cosmic playground merry-go-round. This process can take millions of years, but eventually the neutron star is spinning so rapidly it pulses hundreds of times per second. These millisecond pulsars are found in globular clusters, dense balls of ancient stars that are over 10 billion years old, far older than typical pulsars. Without the accretion process reviving them, these neutron stars would have gone dark long ago. At the opposite end of the stellar spectrum are the first stars that ever formed. These early giants, called population III stars, were born from the pure hydrogen and helium left over from the Big Bang. Unlike modern stars, they contained essentially no heavy elements, no carbon, oxygen, or iron. This had profound consequences for how they formed and evolved. Without heavier elements to help cool gas clouds through radiation, these primordial clouds had to be much larger and hotter before they could collapse into stars. As a result, the first stars were likely enormous, perhaps 100 to several hundred times the mass of the Sun. They would have been extraordinarily hot and bright, possibly 1,000,000 times more luminous than our Sun, shining with intense ultraviolet radiation. Their lifespans were brief by cosmic standards, perhaps only a few million years. When they exhausted their fuel, many would have exploded as parent stability supernova, explosions so powerful they obliterated the star completely, leaving no remnant behind. Others might have collapsed directly into black holes. These first stars changed the universe. Their intense radiation began ionizing the hydrogen gas that filled space, creating bubbles of clear, ionized regions that gradually merged. This epoch, called reionization, transformed the cosmos from opaque to transparent. Their supernova explosions also seeded the universe with the first heavy elements: carbon, oxygen, silicon, iron. These elements mixed into the surrounding gas, enriching it. The next generation of stars that formed included these heavy elements, allowing them to be smaller and longer-lived. Over billions of years, the universe's metallicity, the proportion of heavy elements, gradually increased. Every generation of stars that lived and died added to this chemical heritage. By the time our Sun formed about 4.6 billion years ago, the gas it condensed from contained about 2% heavy elements by mass. That doesn't sound like much, but it was enough to allow rocky planets like Earth to form. Without the first stars and their sacrificial explosions, we wouldn't be here. No one has directly observed a population III star. They're all long gone, and they formed so far away and so long ago that even our most powerful telescopes struggle to see them. But recent observations from the James Webb Space Telescope have found hints. In 2024, astronomers announced the possible detection of dark stars, enormous objects powered not by fusion but by dark matter annihilation. If dark matter particles were captured by gravity in the first dense gas clouds, their annihilation could have released enough energy to create glowing objects far larger than normal stars. These would have been the earliest lights in the universe, short-lived but spectacular. The James Webb Telescope has also found extremely bright galaxies in the early universe that shouldn't exist according to standard models. These galaxies formed when the cosmos was less than 500 million years old, and they're so luminous and massive that they suggest star formation in the early universe was far more efficient than expected. Perhaps population III stars formed more quickly and prolifically than models predict. Or perhaps these bright early galaxies contained supermassive black holes that grew impossibly fast. These discoveries are pushing our theories to their limits, forcing astronomers to reconsider assumptions about how the first structures formed. Stars, whether massive blue giants or tiny red dwarfs, whether pulsars or magnetars or the theoretical dark stars of the earliest cosmos, all share a common origin in collapsing clouds of gas and a common fate of transformation. They live, burn, and ultimately return their enriched material to space. In this way, stars are not just lights in the darkness, but factories for complexity, engines that build the periodic table one fusion reaction at a time. Every atom in your body except hydrogen was forged inside a star or during a supernova explosion. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces and scattered across space when those stars died. In a very real sense, you are made of stardust, and the light from ancient stars billions of years gone still touches you through the atoms they left behind. Black holes in the fabric of spacetime. Among the universe's most enigmatic objects are black holes, regions of spacetime where gravity has become so intense that nothing can escape, not even light. The concept emerged from Einstein's general theory of relativity, published in 1915, which describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Massive objects warp the fabric of space and time around them, and other objects move along the curves created by this warping. For most masses, the curvature is gentle. Earth, for example, creates a slight dip in spacetime, just enough to keep the Moon in orbit. But collapse enough mass into a small enough volume, and the curvature becomes infinite at a central point called a singularity. Surround that singularity with an event horizon, the boundary beyond which escape is impossible, and you have a black hole. Stellar mass black holes form when massive stars, typically those more than about 20 times the Sun's mass, reach the end of their lives. After exhausting their nuclear fuel, their cores collapse catastrophically. If the core is massive enough, not even neutron degeneracy pressure can halt the collapse. The core continues shrinking, crushing neutrons together, passing through every possible state of matter until it vanishes into a point of infinite density. The outer layers of the star may explode outward as a supernova, or they may fall inward to join the black hole, depending on the details of the collapse. What remains is an object from which no information can escape. Everything that falls past the event horizon is lost from the perspective of outside observers, frozen at the horizon in a kind of gravitational photograph that fades over time due to Hawking radiation. Black holes aren't entirely black. In 1974, Stephen Hawking predicted that quantum effects near the event horizon should cause black holes to emit faint radiation, gradually losing mass over incomprehensibly long timescales. Near the horizon, particle-antiparticle pairs spontaneously form and annihilate, as they do everywhere in space due to quantum fluctuations. But at the horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real, carrying away a tiny bit of energy and reducing the black hole's mass infinitesimally. For a black hole with the mass of the Sun, the temperature of this Hawking radiation would be about a 10 millionth of a degree above absolute zero, far colder than the cosmic microwave background. Such a black hole wouldn't evaporate. It would actually grow by absorbing background radiation faster than it radiates. Only black holes much less massive than the Sun, perhaps the size of an asteroid, would be hot enough to lose significant mass through Hawking radiation. If any such primordial black holes formed in the early universe, the smallest ones might be evaporating right now in final bursts of gamma rays. But we've never detected such an event, and it's unclear whether small primordial black holes exist at all. The existence of black holes remained theoretical until 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from two black holes spiraling together and merging. This discovery, announced in February 2016, provided direct evidence for black holes and opened an entirely new way of observing the cosmos. Gravitational waves are ripples in spacetime itself, predicted by Einstein but never directly detected until LIGO's triumph. When two massive objects orbit each other at very close range, they create waves that propagate outward at the speed of light, carrying energy away from the system and causing the orbit to gradually shrink. As black holes spiral closer, the gravitational waves grow stronger and arrive more frequently, creating a characteristic chirp signal that rises in pitch until the objects merge. LIGO detected this chirp on September 14, 2015. The signal lasted less than a quarter of a second, but contained more information than decades of astronomical observation could have provided. The two black holes were 29 and 36 times the mass of the Sun, and they merged to form a single black hole of 62 solar masses. 3 solar masses worth of energy were converted directly into gravitational waves, more power than all the stars in the observable universe emit in light during the same brief time. Since that first detection, LIGO and its partners Virgo in Italy and KAGRA in Japan have detected over 100 gravitational wave events. Most come from black hole mergers, though a few involve neutron stars or mixed black hole neutron star pairs. Each detection teaches us something new. The masses and spins of black holes, measured from the gravitational wave signals, reveal how they formed. Black holes with low spins likely formed from single stars that collapsed directly. High-spin black holes might result from mergers, with the angular momentum of the orbital motion being converted into rotation of the final remnant. The distribution of masses helps constrain theories of stellar evolution and supernova. And the rate at which these mergers occur tells us about the density of black holes in the universe and how often binary black hole systems form. One of the most remarkable recent detections is GW2 50114, recorded on January 14, 2025. This signal stands out as the clearest gravitational wave ever measured, about 4 times more distinct than the original 2015 discovery. The improved signal quality allowed scientists to perform tests that were previously impossible. For the first time, they confidently identified 2 distinct tones in the ringdone phase, the brief period after the merger when the newly formed black hole settles into its final state, vibrating like a struck bell. These tones, or modes, are characteristic vibrations predicted by general relativity, and measuring them provides a direct test of Einstein's equations in the most extreme conditions imaginable. The data match the predictions beautifully, confirming that black holes behave exactly as general relativity predicts, even when spacetime is warped almost beyond comprehension. The same signal also provided strong evidence for Hawking's area theorem. In 1971, Stephen Hawking proved mathematically that if general relativity is correct, the surface area of a black hole's event horizon can never decrease, even during a merger. As 2 black holes combine, the final black hole's area must be at least as large as the sum of the 2 original areas. This is similar to the second law of thermodynamics, which states that entropy, a measure of disorder, never decreases in a closed system. Indeed, black hole area is directly related to entropy. For GW2 50114, scientists measured the masses and spins of both black holes before the merger and calculated their event horizon areas. They then measured the mass and spin of the final black hole and calculated its area. The final area was indeed larger, confirming Hawking's theorem with unprecedented precision. It's a powerful validation of our understanding, linking quantum mechanics, thermodynamics, and general relativity in a profound way. Gravitational wave observations also reveal that massive black hole mergers are common. The universe is full of these events, dozens happening every year just within the range of our current detectors. As LIGO and its partners undergo upgrades to increase their sensitivity, they'll detect more distant and less powerful events. Future detectors, like the European Space Agency's Laser Interferometer Space Antenna, LISA, planned for launch in 2035, will observe gravitational waves from supermassive black hole mergers, events that occur when entire galaxies collide. These signals will be much lower in frequency, lasting months or years instead of fractions of a second. LISA will also be able to detect extreme mass ratio inspirals, where a small black hole spirals into a supermassive one over the course of years, tracing out millions of orbits. Each orbit provides information about the spacetime near the massive black hole, creating a detailed map of the gravitational field. If there's dark matter concentrated around these supermassive black holes, as some theories predict, the small black hole's orbit will be subtly affected. By carefully measuring the gravitational wave signal, LISA might detect these effects and reveal the distribution of dark matter in galactic centers. The future of gravitational wave astronomy is bright. Within the next decade, we'll likely detect the first signals from cosmic strings if they exist, one-dimensional defects in spacetime left over from the early universe. We might find evidence of exotic compact objects that aren't quite black holes but something even stranger. We'll almost certainly observe events we haven't anticipated, phenomena no one predicted. That's the nature of opening a new window on the universe. Before LIGO, we explored the cosmos with light and particles. Now we can feel the vibrations of spacetime itself, sensing the universe's most violent events through the fabric of reality. It's a profound shift in perspective, one that Einstein himself never fully expected to see realized. General relativity was his most elegant achievement, but even he doubted gravitational waves would ever be detected. They're simply too faint, the ripples too small. Yet human ingenuity prevailed. By building detectors sensitive enough to measure distortions thousands of times smaller than a proton, scientists turned the impossible into routine. Every detection is a triumph, a reminder that the universe rewards patience and precision with revelations. Galaxies near and far. Galaxies are the universe's fundamental building blocks, vast collections of stars, gas, dust, and dark matter bound together by gravity. Our Milky Way contains several 100 billion stars, stretching about 100,000 light-years across its luminous disk. But that visible disk is just the bright center of something much larger. Surrounding it is a roughly spherical halo of dark matter, ancient stars, and globular clusters that extends perhaps 500,000 light-years or more, 10 times the diameter of the visible galaxy. This dark halo is where most of the Milky Way's mass resides, the invisible scaffolding that holds the whole structure together and dictates how stars orbit within it. The Milky Way didn't form all at once. It grew over billions of years through countless mergers with smaller galaxies, gradually assembling its current mass. We can still see evidence of this violent past in streams of stars stretched across the sky, remnants of dwarf galaxies that wandered too close and were torn apart by tidal forces. The Sagittarius Dwarf Elliptical Galaxy is currently being consumed by the Milky Way, its stars being pulled out in long streamers that wrap around our galaxy multiple times. Eventually, these stars will be fully integrated, and all trace of the original galaxy will be erased. It's happening slowly, over hundreds of millions of years, but it's happening now. The Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, are also doomed to this fate. In about 2.4 billion years, the Large Magellanic Cloud will collide with the Milky Way, likely triggering a burst of new star formation as gas clouds compress and collapse. The Small Magellanic Cloud will follow later. These interactions will reshape our galaxy, possibly disturbing the solar system's orbit, though Earth itself should survive the encounters unscathed. But an even grander collision looms in the more distant future. The Andromeda Galaxy, our nearest large galactic neighbor, is approaching at about 110 kilometers per second. Right now it's about 2.5 million light-years away, but that gap is closing. In approximately 4 billion years, give or take, Andromeda and the Milky Way will begin to interact. The first close passage will likely be chaotic, with both galaxies' shapes distorted by tidal forces, stars and gas thrown into long tails and bridges. The two galaxies might pass through each other, then swing back for a second collision. Eventually, they'll merge completely, forming a single elliptical galaxy that astronomers have whimsically named Milkomeda or Milkdromeda. Individual stars will almost never collide. Space between stars is so vast that even during a galactic merger, stars simply pass by each other. But gas clouds will collide, compress, and ignite in bursts of star formation. The central supermassive black holes, one in each galaxy, will eventually spiral together and merge, creating a single black hole tens of millions or even hundreds of millions of times the Sun's mass. What will happen to Earth and the solar system during this merger? Most likely, nothing dramatic. The Sun will be nearing the end of its main sequence lifetime by then, gradually brightening and making Earth less habitable. The galactic merger itself will have minimal direct impact on the solar system. There's a small chance Earth could be ejected from the galaxy entirely if a close stellar encounter disrupts the Sun's orbit, but this is unlikely. More probably, the Sun will simply end up in a different location within the merged galaxy, perhaps farther from the center or embedded in a different stellar population. The night sky will change dramatically during the merger. Andromeda, currently a faint smudge barely visible to the naked eye, will grow larger and brighter over millions of years, eventually stretching across a significant portion of the sky. New star-forming regions will ignite, blue and bright. The Milky Way's familiar band of light will distort and fragment as tidal forces reshape the galactic disk. For any beings alive on Earth at that time, if life persists, the sky will be a spectacular canvas of galactic chaos, a celestial display unlike anything visible today. While Andromeda and the Milky Way represent our local future, the James Webb Space Telescope has been revealing the distant past, observing galaxies as they appeared when the universe was young. In 2024, JWST detected galaxies that formed just 200 million years after the Big Bang, during what's called the cosmic dawn. These early galaxies are surprisingly bright and massive, challenging expectations. According to standard models, galaxies should have formed gradually, starting small and growing through mergers. But JWST is finding massive galaxies, some containing billions of stars worth of mass, existing far earlier than theory comfortably allows. One particularly notable discovery is a galaxy candidate observed as it was when the universe was only 270 million years old. This galaxy appears to contain more mass in stars than our Milky Way, yet it formed in a fraction of the time the Milky Way took to assemble. If these observations are correct, it suggests star formation in the early universe was far more efficient than current models predict. What could explain these massive early galaxies? Several possibilities are being explored. Perhaps the first stars, those population III giants, were even more massive and short-lived than thought, converting gas into stars at a prodigious rate. Or maybe the early universe experienced periods of exceptionally intense star formation triggered by the first galaxy's interactions and the radiation from the first black holes. Some astronomers have proposed more exotic explanations, like primordial black holes seeding galaxy formation earlier than expected, or even modifications to dark matter physics that allow structures to form more quickly. Another possibility is that these observations are being misinterpreted. The objects might not be as massive as they appear. Perhaps we're seeing light from extremely luminous but less massive galaxies, or maybe foreground dust is making distant objects appear redder and thus more distant than they actually are. Additional observations and careful analysis will be needed to resolve these questions. JWST has also provided unprecedented views of galaxy structure in the early universe. Unlike the smooth, well-organized spiral galaxies common in today's cosmos, many early galaxies appear clumpy and irregular, with star formation concentrated in a few bright knots rather than spread across a disk. This aligns with expectations. Galaxies in the early universe were undergoing rapid mergers and accretion, constantly disturbed by interactions. The smooth spirals we see today took billions of years to develop, settling down as the universe aged and major mergers became less frequent. Some of these early galaxies also show evidence of powerful outflows, gas and dust being blown out at thousands of kilometers per second by supernova explosions or radiation from central black holes. These winds can enrich the surrounding intergalactic medium with heavy elements, seeding future generations of star formation, or they can suppress star formation within the galaxy itself by removing the raw material needed to make new stars. Not all galaxies shine brightly. Some are extraordinarily faint, containing very few stars despite having substantial mass in gas and dark matter. These ultra-diffuse galaxies stretch across tens of thousands of light years, but emit less light than much smaller galaxies. Some appear to be failed galaxies, systems that never managed to form many stars despite having all the ingredients. Perhaps they were heated too early by the ultraviolet radiation from the first stars, preventing gas from cooling and collapsing. Others might have had their gas stripped away by ram pressure as they moved through the hot gas in galaxy clusters. A few ultra-diffuse galaxies seem to contain almost no dark matter at all, which is puzzling because dark matter is supposedly essential for galaxy formation. These dark matter-free galaxies might be tidal remnants, pieces torn off larger galaxies during close encounters. Or they could represent a new class of galaxy we don't yet understand. Then there are quasars, among the most luminous objects in the universe. A quasar is a galaxy with an extraordinarily active supermassive black hole at its center. As matter falls toward the black hole, it forms an accretion disk, a swirling pancake of gas heated to millions of degrees. The disk glows brilliantly across the electromagnetic spectrum, often outshining all the stars in the host galaxy combined. Some quasars emit jets, narrow beams of particles accelerated to near light speed and shot out perpendicular to the disk. These jets can extend for millions of light years, carving enormous lobes in the surrounding intergalactic medium. Quasars were more common in the early universe when galaxies were smaller and gas was more abundant. Today, most supermassive black holes are relatively quiet, including the one at the Milky Way's center, which glows only faintly as occasional small clumps of gas wander too close. But in the distant past, the universe was ablaze with quasars, beacons visible across billions of light years. The supermassive black holes powering quasars pose their own mystery. These objects can be billions of times the sun's mass, yet some exist when the universe was less than 1 billion years old. How did they grow so large so quickly? Black holes grow by accreting matter, but there's a limit to how fast they can do this. As matter falls in, it heats up and radiates intensely. This radiation pushes back on the infalling gas, creating a balance called the Eddington limit. A black hole can grow roughly exponentially, doubling its mass every few tens of millions of years, but starting from a stellar mass black hole of a few tens of solar masses. It would take hundreds of millions of years to reach 1 billion solar masses, even under ideal conditions. Yet we observe billion solar mass black holes when the universe was only 600 million years old. Either they started much larger than stellar mass black holes, perhaps forming directly from the collapse of massive gas clouds in the early universe, or they found ways to accrete faster than the Eddington limit allows. Recent simulations suggest that in the dense environments of the early universe, black holes could have merged frequently, growing rapidly through collisions rather than just accretion. This remains an active area of research. Galaxies, whether nearby spirals, distant quasars, or faint ultra-diffuse systems, collectively paint a picture of cosmic evolution. They form in the densest regions of the cosmic web, where dark matter halos collapse and draw in gas. They grow through star formation and mergers. They're shaped by feedback from supernova and black holes, and eventually, in the far future, they'll exhaust their gas supplies and fade, leaving behind aging stellar populations that slowly cool. But for now, in this epoch of the universe, galaxies are vibrant, diverse, and full of activity. They're the cities of the cosmos, where stars are born, live, and die, where black holes lurk, and where the chemistry necessary for life is forged. We live within one such city, a spiral galaxy of modest size, orbiting about 2/3 of the way out from the center in a relatively quiet neighborhood. From our vantage point, we look out at countless other galaxies, each a universe unto itself, each containing billions or trillions of stars and uncounted worlds. The night sky is a reminder that we're part of something vastly larger, a single thread in an enormous cosmic tapestry woven from light and gravity across billions of years. The cosmic timeline. To understand the universe, we must understand its history, the long arc from the Big Bang to the present and beyond. The story begins about 13.8 billion years ago in a state of unimaginable density and temperature. We call this the Big Bang, though the name is somewhat misleading. It wasn't an explosion in space, but rather the beginning of space itself, along with time and all the energy that would eventually become matter. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, growing from smaller than an atom to perhaps the size of a grapefruit in about 10 to the minus 35 seconds. This inflationary burst smoothed out irregularities and stretched tiny quantum fluctuations to cosmic scales, creating the seeds of future structure. After inflation ended, the universe continued expanding but at a slower rate. It was filled with a hot, dense soup of fundamental particles, quarks, leptons, photons, all in thermal equilibrium. As it expanded and cooled, quarks combined to form protons and neutrons. About 3 minutes after the Big Bang, the temperature dropped enough for nuclear fusion to occur, creating the first light atomic nuclei, mostly hydrogen with some helium and trace amounts of lithium and beryllium. This process, called Big Bang nucleosynthesis, lasted only a few minutes but determined the universe's chemical composition for hundreds of millions of years. For the next 380,000 years, the universe remained opaque. Photons couldn't travel far before scattering off free electrons, but as the temperature dropped, electrons and protons combined to form neutral hydrogen atoms in a process called recombination. Suddenly, light could travel freely. The photons that decoupled at this moment have been traveling ever since, stretched by cosmic expansion from visible wavelengths into microwaves. We detect them today as the cosmic microwave background, a faint glow at a temperature of 2.7 Kelvin, just above absolute zero. This radiation carries a wealth of information about the early universe. Tiny temperature variations, about 1 part in 100,000, reveal the density fluctuations that would eventually grow into galaxies and clusters. By carefully mapping these variations, scientists have determined the universe's age, composition, and geometry with remarkable precision. The cosmic microwave background is one of the most important pieces of evidence supporting the Big Bang model and cosmology's best tool for studying the infant universe. After recombination, the universe entered a period called the cosmic dark ages. Stars hadn't formed yet, and with no light sources, the universe was filled only with cooling hydrogen gas and the fading glow of the cosmic microwave background. This era lasted for about 100 million years, a time of cold darkness punctuated only by the gradual clumping of matter under gravity. Dark matter halos collapsed first, drawing in ordinary gas, and within these halos the first stars began to form. These population III stars, discussed earlier, were massive, hot, and short-lived. Their light began ionizing the surrounding hydrogen, creating bubbles of transparency that gradually grew and merged. This epoch of reionization transformed the universe from neutral and opaque to ionized and transparent, the state it remains in today. Reionization was complete by about 1 billion years after the Big Bang, and by this time, the first galaxies had assembled, small, irregular systems rich in gas and actively forming stars. The next several billion years saw the peak of cosmic star formation. Galaxies merged and grew, dark matter halos became more massive, and gas was funneled into galactic centers where it collapsed into stars at a prodigious rate. This epoch, from about 1 to 4 billion years after the Big Bang, was the universe's stellar springtime, the period when most stars that have ever existed were born. Our sun formed much later, about 9 billion years after the Big Bang, in a galaxy that by then had settled into a relatively stable spiral structure. By the time Earth formed, the universe had already aged considerably, and many of the most dramatic events of cosmic history were in the past. Today, about 13.8 billion years after the Big Bang, we live in a relatively calm era. Star formation continues, but at a much reduced rate compared to the peak. Galaxies are more mature, their structures well-defined, and mergers, while still occurring, are less common. Dark energy has taken over as the dominant component of the universe, driving accelerating expansion. The night sky is filled with galaxies, but they're receding, slowly moving apart as space grows. In the far future, this expansion will carry most galaxies beyond our observational reach. 100 billion years from now, the Milky Way and Andromeda, having merged into Milkomeda, will be surrounded by darkness. The cosmic microwave background will have cooled to a fraction of a degree above absolute zero, undetectable by any practical means. And the universe will have entered a new phase, one where star formation has largely ceased and existing stars are aging. The far future of the universe depends on the nature of dark energy. If dark energy remains constant, as current data suggest, the universe will expand forever, cooling into a state called heat death. Stars will exhaust their fuel and die. White dwarfs will cool into black dwarfs, though this will take trillions of years. Neutron stars and black holes will persist even longer, but eventually, even black holes will evaporate through Hawking radiation, leaving behind only elementary particles drifting through an ever-expanding void. The process will be extraordinarily slow. A solar mass black hole will take about 10 to the 67 years to evaporate, far longer than the current age of the universe. Supermassive black holes will take even longer, perhaps 10 to the 100 years. After they're gone, all that will remain are photons, neutrinos, and occasional particle-antiparticle pairs popping into existence and annihilating, quantum fluctuations in a universe grown cold and empty. There's a kind of peacefulness to this fate, a gradual fading rather than a catastrophic end, a universe that whispers itself into eternal silence. Alternative fates are possible if dark energy evolves. If dark energy's density increases over time, it could lead to a big rip, where the accelerating expansion eventually tears apart galaxies, then stars, then planets, and finally atoms and even atomic nuclei. This would be a violent end, though still billions of years away. Conversely, if dark energy weakens and reverses, the expansion could slow, stop, and reverse, leading to a big crunch where the universe collapses back into a hot, dense state. Some theories even propose a cyclic universe where each big crunch is followed by a new Big Bang, an endless series of expansions and contractions. There's currently no strong evidence for these alternatives, but they remain possibilities, reminders that despite our advances, we still don't fully understand the universe's ultimate fate. What we do know is that we're fortunate to live when we do. The universe is still filled with stars, galaxies are still visible across vast distances, and the cosmic microwave background is still detectable. Intelligent civilizations arising in the far future, if any exist, will have a much harder time reconstructing cosmic history. They'll see only their local galaxy surrounded by emptiness, the cosmic microwave background cooled to undetectability, and no evidence of the Big Bang or the early universe. We, by contrast, can look back across most of cosmic history, observing galaxies at every stage of evolution, studying the cosmic microwave background, detecting gravitational waves from black hole mergers billions of light years away. We're living in an age of cosmic enlightenment, a brief window in which the universe is old enough to have produced complex structures and intelligent life, but young enough that the evidence of its origin remains accessible. It's a gift, this moment in time, this opportunity to understand where we came from and where we're going. Has strange phenomena across the cosmos. The universe is full of phenomena that challenge intuition and stretch imagination. Consider rogue planets, worlds that drift through space without stars. These aren't science fiction, they're real and likely numerous. Most planets form within protoplanetary disks around young stars, but gravitational interactions can eject them. In a young star system with multiple giant planets, the planet's orbits can become unstable, leading to close encounters where one planet gets flung outward at high speed, escaping the star's gravity entirely. Other rogue planets might form independently, collapsing from gas clouds like stars but too small to ignite fusion. These objects would be cold, dark, and nearly invisible unless they passed directly in front of a background star, briefly magnifying its light through gravitational microlensing. Astronomers estimate there could be billions of rogue planets in the Milky Way, possibly outnumbering stars. These worlds drift alone through the darkness, orbiting the galaxy itself rather than any sun, experiencing eternal night broken only by faint starlight. Some might harbor subsurface oceans kept liquid by geothermal heat or radioactive decay, theoretical habitats for life that would exist in perpetual darkness. Then there are diamond planets, worlds composed largely of carbon rather than the silicate rocks and iron that dominate Earth. In star systems unusually rich in carbon relative to oxygen, planets that form can have exotic compositions. Under immense pressure and temperature, carbon crystallizes into diamond. The first candidate diamond planet was discovered orbiting a pulsar, a rapidly spinning neutron star. Based on the planet's mass and radius, scientists calculated its density and concluded it must be primarily crystalline carbon, essentially a planet-sized diamond. Of course, it wouldn't sparkle like a jewel. Surface temperatures likely exceed 1200 degrees Celsius, and there's no atmosphere to scatter light. But deep within, stretching perhaps thousands of kilometers down, lie lattices of diamond, a world built from the material we treasure most rarefied into planetary scale. Closer to home, though still far away, the moon is gradually abandoning us. Each year, it recedes about 3.8 centimeters from Earth. This happens because of tidal interactions. The moon's gravity creates bulges in Earth's oceans, the tides. As Earth rotates, these bulges are carried slightly ahead of the line between Earth and the moon. The gravitational pull of these leading bulges tugs on the moon, accelerating it very slightly in its orbit. This acceleration increases the moon's orbital energy, causing it to spiral slowly outward. Simultaneously, the interaction slows Earth's rotation. Days are getting longer by about 1.7 milliseconds per century. This process has been occurring since the moon formed about 4.5 billion years ago, likely from debris ejected when a Mars-sized object collided with the young Earth. Back then, the moon was much closer, perhaps 20,000 kilometers away compared to today's 384,000 kilometers. Tides were enormously more powerful, and Earth's day was only about 5 hours long. Over billions of years, the moon has drifted to its current distance, and it will continue moving away. Eventually, tens of billions of years from now, Earth and the moon will become tidally locked to each other, each always presenting the same face to the other, and the moon's recession will cease. But by then, the sun will have long since swollen into a red giant, likely engulfing both Earth and the moon, rendering these calculations moot. The cosmic microwave background, that faint glow from the early universe, contains its own mystery, a cold spot. In 2004, astronomers analyzing data from the Wilkinson Microwave Anisotropy Probe noticed a large region where the temperature is about 70 microkelvin colder than the surrounding sky. This doesn't sound like much, but it's significantly colder than expected from random fluctuations. The cold spot spans about 5 degrees across, about 10 times the apparent size of the full moon. Several explanations have been proposed. It might be a supervoid, an enormous region with lower than average matter density. Light passing through such a void would lose energy climbing out of the gravitational potential well, getting redshifted and appearing colder. But the void would need to be incredibly large, hundreds of millions of light years across, and it's unclear whether such large voids existed when the cosmic microwave background photons last scattered. Another idea is that the cold spot represents a collision between our universe and another universe during the inflationary epoch, a kind of cosmic bruise. This is speculative and difficult to test, but it's not impossible. The cold spot remains one of cosmology's outstanding puzzles, a feature that doesn't quite fit, a whisper that something about our understanding might be incomplete. Space itself is anything but empty. Even in the darkest voids between galaxies, where matter density is vanishingly small, quantum physics tells us that empty space seethes with activity. Particle-antiparticle pairs constantly pop into existence and annihilate, fluctuations permitted by Heisenberg's uncertainty principle. These virtual particles can't be directly observed, but they affect measurable quantities like the Casimir effect, where two uncharged metal plates in a vacuum experience an attractive force because fewer virtual particles fit between the plates than outside them. This quantum foam, as it's sometimes called, has real consequences. It contributes to the vacuum energy that might be driving dark energy and cosmic acceleration. The energy density of the vacuum is extraordinarily small, but multiply it by the volume of the entire universe, and it becomes significant enough to influence the fate of the cosmos. Some phenomena are more visible but no less strange. Gravitational lensing can create multiple images of the same distant object, smeared into arcs or even complete rings called Einstein rings. Occasionally, a supernova in a distant galaxy will be lensed by an intervening galaxy cluster, and its light will arrive via multiple paths with different travel times. Astronomers have observed the same supernova explode in multiple locations in the sky, months or years apart, as light taking different routes through warped spacetime arrives at Earth. This allows precise measurements of the expansion rate of the universe and the distribution of dark matter in the lensing cluster. It also creates eerie images where the same event is frozen at different moments, a single star's death replayed across the sky like echoes of light. Binary stars, two stars orbiting each other, can create their own spectacles. If the stars are close enough, they can transfer mass between them, one star spilling gas onto its companion. Sometimes this transfer is steady, creating an accretion disk and potentially leading to nova eruptions when enough material accumulates on the surface of a white dwarf to ignite fusion. Other times, the transfer is catastrophic, leading to a merger. When two white dwarfs merge, the result might be a type Ia supernova, a thermonuclear explosion that briefly outshines the entire galaxy. These supernovae are remarkably uniform in brightness, making them excellent distance markers for measuring cosmic expansion. When two neutron stars merge, the result is a kilonova, an explosion that produces heavy elements like gold, platinum, and uranium through rapid neutron capture. The 2017 detection of gravitational waves from a neutron star merger, followed by observations across the electromagnetic spectrum, confirmed that these events are the primary sources of the heaviest elements in the universe. Stars can also sing in a manner of speaking. They undergo oscillations, pressure waves that travel through their interiors, causing their surfaces to pulsate. By measuring these oscillations, astronomers can probe a star's internal structure, determining its size, mass, age, and composition. This field, called asteroseismology, has been applied to thousands of stars, including our Sun. The Sun rings with millions of different frequencies simultaneously, like a vastly complex organ. Some oscillations take 5 minutes to complete, others hours or days. By analyzing these vibrations, scientists have mapped the Sun's interior, discovering layers where convection occurs, zones where sound speed changes, even regions where the Sun's rotation rate varies with depth. This technique has been extended to other stars, allowing precise characterization of exoplanet hosts and helping calibrate stellar evolution models. The poetry of spacetime. There's a certain poetry to the way light travels across the universe. Photons emitted by distant galaxies billions of years ago are still journeying toward us, carrying information about a cosmos that no longer exists in that form. When you look at a galaxy 10 billion light years away, you're not seeing it as it is now, but as it was 10 billion years ago, when the universe was less than a quarter of its current age. That galaxy has changed since then. Its stars have evolved. Some exploded new stars have formed. Perhaps it merged with another galaxy. But the light reaching your eyes tonight began its journey when those ancient events were just unfolding. In a very real sense, telescopes are time machines, allowing us to observe the past directly. Deep field images from Hubble or James Webb are galleries of cosmic history, with nearby galaxies appearing as they are recently and distant galaxies frozen in their youth. Consider that the atoms in your body were forged in stars, Not the sun, but earlier generations of stars that lived and died before the sun even formed. The hydrogen in your body, the most abundant element, dates back to the Big Bang itself, created in the first 3 minutes when the universe was a hot, dense plasma. But the heavier elements, carbon, nitrogen, oxygen, iron, phosphorus, everything else, were manufactured inside stars through nuclear fusion and then scattered into space by supernova explosions. Those atoms drifted through the galaxy for millions or billions of years, mixing with gas clouds, collapsing again into new stars and their accompanying planets. About 4.6 billion years ago, a particular cloud in the Milky Way's outskirts began to collapse. Most of the mass fell into the center, igniting as the sun, but the remaining material formed a disk where planets coalesced. Earth grew from countless collisions of smaller bodies, asteroids and planetesimals, each one carrying atoms from previous stellar generations. Over hundreds of millions of years, Earth's surface cooled, water condensed, and chemistry became complex enough for life to emerge. Every living thing on this planet is built from recycled stardust, atoms that once burned in stellar cores or were synthesized in supernova shock waves. You are, quite literally, the universe made conscious, a temporary arrangement of ancient atoms complex enough to ponder its own existence. This connection goes deeper than chemistry. The universe, through you, is observing itself. For billions of years, the cosmos existed without awareness, stars born and dying, galaxies colliding, black holes merging, all happening in the dark without witness. Then on at least one planet and perhaps countless others, matter organized itself into structures capable of perception and thought. Through your eyes, the universe sees itself. Through your mind, it contemplates its own nature, origin, and fate. This is not metaphor but fact. The atoms that form your neurons were created in stars. The energy powering your thoughts comes from food, which derives ultimately from sunlight, stellar fusion converted through photosynthesis into chemical energy. The patterns your brain creates, thoughts, memories, dreams, are emergent properties of matter and energy governed by the same physical laws that shape galaxies and guide the expansion of space. You are not separate from the cosmos but an intimate part of it, a brief flourishing of complexity in an evolving universe. There's beauty in scales both large and small. The largest structures we know, filaments and superclusters of galaxies stretching across hundreds of millions of light years, mirror and form the network of neurons in a human brain. Both exhibit similar statistical properties, nodes connected by threads, forming networks without central control. Of course, the resemblance is coincidental, arising from different underlying physics, but it hints at deep principles governing complex systems. Similarly, the quantum fluctuations that seeded all cosmic structure were unimaginably tiny, variations in energy density at scales far smaller than an atom. Yet inflation stretched these fluctuations to cosmic proportions, imprinting them on the distribution of matter across the universe. The grandest structures in existence trace their lineage back to the smallest possible perturbations. This interplay between the microscopic and the cosmic runs throughout physics. General relativity describes gravity and spacetime on the largest scales. Quantum mechanics governs the smallest. Reconciling these theories, finding a quantum theory of gravity, remains one of physics' great challenges. Success would unite our understanding of the very large and very small, revealing the universe as a single coherent system operating according to consistent principles. Light, that familiar phenomenon we experience every day, is also a mystery. Photons have no mass, yet they carry energy and momentum. They always travel at the speed of light in a vacuum. About 299,792,458 meters per second, but they experience no passage of time. From a photon's perspective, if it could have one, its emission and absorption are simultaneous, no matter how far it travels through space. A photon emitted by a star a billion light years away experiences no subjective time during its journey. It exists at all points along its path simultaneously from its own frame of reference. Only we, observing from outside, see it as taking time to travel. This is a consequence of relativity. As an object approaches the speed of light, time dilation becomes extreme. At exactly the speed of light, time stops entirely. Photons are frozen in a timeless present, connecting every point in the universe they touch in a web of instantaneous experience beyond human comprehension. The universe is also filled with music, if only we know how to listen. Gravitational waves are vibrations in spacetime, ripples that stretch and squeeze space as they pass. Different sources produce different frequencies. Black hole mergers create waves in the tens to hundreds of hertz range, just barely audible if they were sound waves, which they're not. Neutron star mergers produce higher frequency waves. Supermassive black hole mergers in distant galaxy collisions will produce waves in the millihertz to microhertz range, far below human hearing but detectable by future space-based observatories. These waves carry information about the events that created them, encoding the masses, spins, and distances of merging objects in the pattern of vibration. By detecting and analyzing gravitational waves, we're learning to hear the universe, sensing it through a channel beyond light and particles, listening to the fundamental oscillations of space itself. Even silence has structure. The cosmic microwave background, though uniform to the naked eye, contains subtle variations that tell a story. Regions that were slightly denser at recombination, where a bit more matter had accumulated, appear slightly warmer. Regions that were less dense appear cooler. These variations, mapped across the entire sky, reveal the seeds of future galaxies and clusters. They also tell us about the universe's composition, age, and fate. The pattern of fluctuations depends on physics operating in the first fraction of a second after the Big Bang, during inflation. By measuring this pattern precisely, cosmologists can test theories of inflation, constrain the properties of dark matter and dark energy, even search for evidence of phenomena like cosmic strings or extra dimensions. The cosmic microwave background is a Rosetta Stone for cosmology, a single dataset that unlocks answers to dozens of fundamental questions. And it's everywhere, a faint glow surrounding us at all times, the oldest light in the universe, still carrying its message across 13.8 billion years of space and time. Closing thoughts. We've traveled far tonight, from the quantum foam of empty space to the largest structures in the universe, from the first moments after the Big Bang to the distant future when stars will have exhausted their fuel and darkness reclaims the cosmos. We've contemplated black holes that warp spacetime into knots, neutron stars spinning faster than blender blades, galaxies colliding and merging over billions of years, and dark matter streaming silently through everything, including you, right now as you rest here. We've seen how light carries history across the universe, how atoms remember their stellar origins, and how the universe has grown eyes in us and countless other possible civilizations, becoming aware of itself through the very matter and energy that comprise it. The universe is vast beyond comprehension, but it's also knowable. Through patient observation, careful reasoning, and ingenious instruments, we've mapped cosmic history from the first fraction of a second to the present. We've discovered that 95% of the universe's content is invisible, that space itself is accelerating outward, that gravitational waves ripple through the fabric of reality, carrying news of cataclysms across billions of light years. We've found planets around other stars, listened to the ringing of dying stars, and captured the shadow of a black hole. Each discovery raises new questions, deepens the mystery even as it provides answers. This is the beauty of science, an endless journey where every answer opens new horizons, where wonder never diminishes but only grows richer, more textured as we learn more. Follow and subscribe for more space journeys.